Hello, everyone, and welcome to today's presentation, HydroPatterns, Advancing Open Surface Water Monitoring in Alberta with Artificial Intelligence and Remote Sensing. Before we begin, I'd like to start with the land acknowledgement. The ABMI respectfully acknowledges that our work takes place on the territories of Treaties 4, 6, 7, 8, 10, and the Métis homeland, traditional and ancestral lands of First Nations and Métis peoples, whose histories, languages, and the cultures are directly linked to the biodiversity that we monitor. We acknowledge the traditional teachings of the lands that we work on and that reciprocal, meaningful, and respectful relationships with Indigenous peoples make our work possible. We are deeply grateful for their stewardship of these lands, and we are committed to supporting Indigenous-led monitoring programs while learning Indigenous ways of knowing, being, and doing. And now, a bit about our presenter today, Thuy Don. So Thuy is a remote sensing scientist at the ABMI with a background in grassland ecology. She began her career applying remote sensing and GIS techniques to develop vegetation management plans, conserve the iconic plains bison, and map the remaining native grasslands in the Saskatchewan prairies. In April 2023, Thuy joined the Earth Observations Insight Unit with the ABMI's Geospatial Center. Since then, she has been working with the team using satellite imagery and a range of geospatial tools and technologies to support habitat mapping and monitoring across Alberta's diverse landscape. Some of her current projects include developing and piloting coarse filter remote sensing indicators and monitoring harmful algal blooms in Alberta lakes. So without further ado, Thuy, please take it away.
Well, thank you very much, Shannon, for the introduction. And thank you everyone for joining the webinar today. Before we jump into my presentation, I've got a little game for you all. It's called Water Wonders, What Changed? The rule is very simple. I will show you two screenshots of a water body taken from space at different times. And your job is to guess what happened to the water body between those two times. Please type your answer into the chat. I hope that's clear, and let's get started with the first water body. The first water body, circled in orange, is located in southeastern McClellan Lake in the Alberta boreal regions. It has size of about 70 hectares. The top image is a screenshot from space in June 2020. The bottom image is a screenshot in July 2020. So from June to July in 2020, a layer of something that had light green color emerged and covered most of the water surface. So my questions for you all is that, what was this light green layer?
All right, Thuy, I'm getting a few chats here. I have someone saying perhaps it's an algae bloom.
Good guess.
Someone says, wow. Duckweed, a guess of duckweed perhaps. Any other guesses? Plant growth? Uh-oh. Perhaps it's some extraterrestrial activity?
Interesting.
Oh, another one here. St. Patrick's Day?
Oh yeah, I love that. Yeah, so thank you everyone who have answers the questions. My answer is aquatic vegetation growth. So like someone said, it can be algae, but it can be a mix of submerged, floating leaf, and emergent plants. Let's come to the second water body. It is Gulf Lake with its boundary in orange color. Gulf Lake is located in the Alberta Parkland regions. From June to July in 2021, a massive amount of white layer has covered the lake. What was this white layer?
Okay, I'm starting to get a few guesses here. Folks are thinking maybe it might be salt or salinity. Again,
we have some ecologists here.
Yeah, perhaps a few people who are wondering if it's aliens again. Comment that, wondering if maybe evaporation is taking place.
Wow, interesting. Yeah, thank you
This is an interesting one. Ash.
Oh wow, yeah. Yes. Yeah, thank you for all of the answers. So my best guess of this white layer is salt. So even though I'm not pretty sure about the reasons behind this change, what I want to emphasize here is that within a very short period of time, as little as a month, significant changes can occur to surface water. And such changes not only influence water uses for many species, including humans, but also play a critical role in shaping ecosystem services. That said, in this HydroPatterns pilot project, we advance open surface water monitoring with AI and remote sensing. I would like to thank Alberta Environment and Protected Areas for providing funding for this work, Ducks Unlimited Canada for providing us a valuable data set for our validation purpose, and also thank both organizations for their valuable input and feedback. This is content of my presentation, including a project overview, introduction on our pilot areas, description of method, and how the HydroPatterns dataset look like, and final messages. As you may know, Alberta has a diverse lentic water systems, including lakes, reservoirs, ponds, dugouts, and wetlands. Alberta experiences ongoing wetland losses and is likely facing a future water crisis. Timely, accurate detection of lentic open surface water can support wetland monitoring, environmental reporting, wetland conservation and reclamation, water management, land use planning. In this project, we set out 3 objectives. First, to develop scalable, efficient, and repeatable lentic open surface water mapping methodologies using remote sensing and machine learning. Second, to generate a mapping dataset of open surface water dynamics or hydropatterns over time and space, primarily for lentic water bodies. And third, to provide recommendations for scaling up province-wide. This product is named HydroPatterns rather than HydroPeriod to reflect a broader focus on all lentic surface water bodies, not limited to wetlands. The HydroPatterns dataset will include a series of monthly open surface water maps for each year, 3 seasonal inundation frequency maps for spring, summer, and fall, a number of annual inundation frequency maps, 1 multi-annual average inundation frequency map, and change detection in total open surface water extent from month to month. Here we define inundation frequency as the percentage of time each pixel is flooded. 2 pilot areas represent environment common across much of the province were chosen. The boreal pilot area encompassing Fort Murray and Fort McKay in the boreal regions, and the prairie pilot area encompassing Stettler in the parkland regions were chosen. Each pilot area covers approximately 5,000 to 6,000 square kilometers. We chose these areas because of their geographical overlap with novel wetland inventory maps, where deep learning, machine learning, and high-resolution airborne LiDAR were used. This is a brand new wetland inventory work with recent recommendations from Alberta Environment and Protected Areas to scale up across Alberta. In both pilot areas, landscape are human disturbed, and between the 2 areas, lentic water bodies vary in characteristics. In the boreal regions, generally, water features are larger with more stable water level. And in the prairies, there are more small water features with fluctuating water levels. Regarding methodology, mapping open surface water dynamics include 2 main steps: open surface water detection at specified times and dynamic assessment. Open surface water detection workflow include 5 mini steps, from image acquisition, pre-processing, training data, validation data collections, to classification and quality controls. In this pilot project, we generated monthly open surface water maps during 2020-2023 growing seasons from May to October. After mapping water presence every month, we stacked all monthly maps and generated the dynamic assessment describing water permanence. For image acquisition and processing, 3 image sources were our input. Sentinel-2 optical image was the primary source that were composited by months. cloud scopers were used to remove cloud and shadows. Water-sensitive indices for each monthly mosaic were also calculated. Due to gaps resulted from cloud scopers, we used the corresponding monthly Sentinel-1 radar to fill in those gaps. Terrain variables, including elevation, slope, and aspect, were also input for modeling. For training data of each pilot area, we generated 10,000 point samples, including water and non-water, using the existing Canada-wide Landsat-based dynamic surface water map. We used stratified random sampling to target more water samples from small water bodies, as these are hard to detect. To quality screen the training dataset, we use an innovative time variable and spectral-based screening process to correct errors at edges or areas where water was not present in a given monthly mosaic. This screening method relies on a principle that waters exhibit constantly low reflectance values. This training data collection method is fully automated, making it efficient for any new areas of interest or Alberta-wide coverage. Here is an example of our screening process where generated water training samples in blue stars were screened their quality. As you may see, 5 water samples were automatically generated from the Canada Landsat-based open surface water dynamic map. When overlaying them on Sentinel-2 monthly mosaic for May 2020, 2 out of 5 water samples were only close to water features, but not water. We observed that these 2 water samples fell within the Sentinel-2 swirl 10 percentile mask. Hence, we use this mask to remove these 2 samples from the training dataset for May 2020. As a result of this screening process, from 10,000 initial samples, the number of training samples actually used for training models varied from mosaic to mosaic and from month to month. To validate the resultant open surface water maps, we use 3 independent validation datasets, 1 for the boreal pilot area and 2 for the prairie pilot area. These datasets were either collected from fieldwork or interpretation of stereo photos or high-resolution satellite images. They have different format, polygon, and point. We use pixel-based accuracy assessment if the validation dataset was polygon-based, and point-based accuracy assessment if validation dataset was point-based. To ensure effectiveness of our approach, we did several testings and then chose pixel-based image analysis and gradient boosting trees classification algorithm. For the information, pixel-based image analysis was found to capture more small water features and be less compute intensive. We produce all monthly Sentinel-1 and Sentinel-2 derived open surface water maps separately. And next, whereas gaps existed in the Sentinel-2 open surface water maps, Sentinel-1 open surface water maps in the corresponding months were used to fill in. We also applied several quality control steps, including removal of isolated spurious pixels or smoothing using a 3x3 majority filter and addressing water commissions errors using a slope mask, an anthropogenic mask, and a vegetation mask. Now comes the most interesting part. How accurate and informative are the HydroPatterns dataset? With our methodology, open surface water was detected with over 90% overall accuracy in both pilot areas. These are the HydroPatterns product in the boreal pilot areas. On the left, you can see seasonal inundation frequency maps. On the right, you can see annual inundation frequency maps. And when zooming in specific areas like McClellan Lake and surrounding wetland complexes, you could see how open water changed from spring to fall in the pattern fence in the southwestern McClellan Lake. Here is the 4-year average inundation frequency map. The graph shows variations of monthly surface water extent. Note that the surface water extent in this graph account for both lithic or flowing and lentic standing habitat. From the graph, there was no clear change in surface water fluctuation in the boreal pilot area. Permanent water accounted for 3% of the landscape, while non-permanent water comprised 6%. And here are the HydroPatterns product in the prairie pilot area, including the seasonal and annual inundation frequency maps. A closer look at the Gatsby Lake natural areas shown in this picture on the right. You can see how open water in southern Gatsby Lake fluctuated from 2020 to 2023. The 4-year average inundation frequency map was shown in the picture on the left, and variation of monthly surface water extent is shown in the graph on the right. As you can see, open surface water extent in the prairie pilot area significantly decreased from year to year and from spring to fall. Permanent water accounted for 4% of the prairie pilot area's landscape, while non-permanent water comprised 7%. The HydroPatterns dataset revealed distinct differences in water spatial stability. For example, a closer look at one permanent lake and one non-permanent lake in the boreal pilot area showed that the permanent lake, here is the McClellan Lake, maintains stable open surface water presence with consistently high inundation frequency, greater than 80%, while non-permanent or recurring lake, here is the Shipyard Lake, showed greater variability and lower average inundation frequencies, less than 65%. An interesting result is that HydroPatterns can detect water extent changes in prairie marshes. As you may know, marshes in the prairie are very dynamic systems where open surface water fluctuates constantly, making them unique for development of different vegetation zones. Knowing how water changes can support wetland classification. We're glad that the HydroPatterns can help visualize such changes. In this example, yellow polygons are the DUC label prairie marshes. Blue color represent open surface water detected by the HydroPatterns monthly open surface water maps. And white circles highlighted areas where water extent varied from May to July in 2020. Moreover, HydroPatterns could track the timing and location of aquatic vegetation growth. Example was shown in the water body near McClellan Lake, circled in yellow here. This is the example I used at the beginning. If you look at the HydroPatterns open surface water maps in June and July 2020, you could see remarkable decrease of open surface water extent. We visually compared the HydroPatterns dataset with the two existing reputable surface water dynamic dataset covering the whole Alberta landscape, including the Canada-wide Landsat-based open surface water dynamic dataset and the Sentinel-1 radar-based hydrotemporal variability. What we found: first, both ABMI's Sentinel-based dataset, including the Alberta hydrotemporal variability and the HydroPatterns, provided an enhanced edges delineation of water features. HydroPatterns could detect more non-permanent water features. This could be explained by the fact that HydroPatterns provided not only interannual but also intra-annual surface water variations. These non-permanent water features identified in the HydroPatterns were likely influenced by the intra-annual variations. Among the two Sentinel-based datasets, Alberta hydrotemporal variability and HydroPatterns, we found that the first dataset contains several errors, and it mostly happened in the prairie pilot areas. For example, many water features were omitted and croplands were misclassified as water. In terms of dataset development, the Alberta hydrotemporal variability dataset experienced lots of human intervention, making it not efficient for reproducibility. The HydroPatterns, fortunately, has addressed both of these issues. We must acknowledge some limitations of our HydroPatterns dataset. The products do not currently distinguish between open surface water in lotic or flowing and lentic habitat. We haven't validated results for lotic habitat yet, as it is not the focus of this pilot project. Additionally, inundated vegetation is not currently accounted for in the workflow or analysis. From a remote sensing perspective, detection of inundated vegetation is challenging with optical imagery, particularly during leaf-on seasons. Sentinel-1 SAR C-band, with its relatively short wavelength, does not reliably penetrate dense shrub and forest canopy. This picture provides you a visual cue of how different radar wavelength can do. A longer wavelength, for example L-band, can penetrate through the vegetation layer and reach the soil surface to collect information. We are patiently waiting for successful launch of a radar L-band sensor named NISA this year and looking forward to using its data for this purpose. For final messages, the HydroPatterns dataset has the following advantages. It has high accuracy detection of water features with enhanced edges delineation. It provides improved temporal metrics, including intra and interannual changes of surface water, hence detects more non-permanent water features. And it addressed omission and commission errors of existing dataset. In this pilot project, we successfully developed a fully automated, scalable, efficient, and reproducible HydroPatterns workflow by integrating a fusion of open access Sentinel imagery, water engines, and machine learning. This workflow is adaptable that can be easily transferred to other satellite imagery input. In the boreal pilot area, lentic open surface water remained stable throughout 2020 to 2023. And in the prairie pilot area, lentic open surface water significantly decreased from year to year and from spring to fall. Some recommendations for Alberta-wide expansion of HydroPatterns. First, we recommend to increase training dataset size in order to account for characteristic variations of Alberta's lentic water bodies. Second, it is necessary to adapt the model for the Rocky Mountains, likely testing, tailoring, because water features here are very limited. Next, use water level data for validation. There is very limited public water level dataset with accurate information of where water level was measured. Hence, we welcome any contributions of such valuable information. If you have relevant data and are interested in collaborating, please feel free to reach out. In addition, we recommend to explore L-band synthetic aperture radar or SAR, such as ongoing PALSAR or upcoming NISA for mapping inundated vegetation. Last but not least, enhancing model transparency with explainable AI to improve model robustness and computational efficiencies, as well as increase transparency in decision making. Here is the list of references I've used in this presentation. Thank you for your attention. I'm happy to answer any questions.
Thank you so much, Thuy.